Finding the limits of basic functions is a relatively trivial pursuit for a basic function such as this one right here. By simply substituting the value of 2 into the function, we find that the limit is equal to 6. Easy. Now let's take a look at a more complicated problem such as this one right here. We run into a problem here with the substitution method. After substituting 4 into the functions, we find the indeterminate 0 divided by 0, and we cannot work directly with it. And not a problem, we have ways of dealing with issues like this. We may simply expand and factorize the function to avoid the 0 divided by 0 mess. Notice that the numerator is a perfect square, so after expanding the function and factorizing out the common factor of x minus 4, so long as x does not equal 4, of course, we find that the limit is equal to 8. Alrighty, that wasn't too hard now, was it? Let's take a look at another function. After substituting 1 in for all the values of x, we once again find the indeterminate 0 divided by 0. Now we could factorize this mess, but I'm not even going to attempt to factorize this. Although factorization may work and we most likely would find the correct answer if we went down that long and winding path, why would we even bother doing all of that work when we have L'Hopital's rule? Simply stated, L'Hopital's rule says that for limits of an indeterminate form, such as the one we just looked at a second ago, the limit can be found by taking the derivative of the functions in question and then finding the limit of this new combination of functions. And L'Hopital's rule does not only apply for 0 divided by 0 cases, it applies for indeterminate cases, which include infinity divided by infinity, or negative infinity divided by negative infinity, and so forth. To put L'Hopital's rule algebraically, where the limit as x approaches a of a function fx over a function gx gives an indeterminate, and where the derivative of the function fx at a exists, and the derivative of the function gx at a exists, and where f quotient a on g quotient a is determinate, then the limit as x approaches a of fx on gx is equal to the limit as x approaches a of f quotient x on g quotient x. That was a mouthful, but L'Hopital's rule is actually much easier to explain practically. So in our previous example involving the quartic function, we may use L'Hopital's rule to find a new set of functions that we can work with. After evaluating these new functions, we find that the limit is negative 2 on 3, and so by extension the limit of the original functions is also negative 2 on 3. It really is that simple. A well-known example of L'Hopital's rule in practice is the old limit as x approaches 0 of sine x on x. Here we once again run into the indeterminate 0 divided by 0. Although we may have been able to solve the quartic function by factorization, here we really have no choice but to use L'Hopital's rule. So, after finding the derivative of the two functions, we have cos x on 1. As x approaches 0, cos x approaches 1, and so the limit is simply 1. Now in some cases, L'Hopital's rule will not lead us directly to a limit, but may take us to yet another indeterminate function, such as this one right here. Now first things first, by substitution we'll simply get an indeterminate infinity divided by infinity scenario. But after applying L'Hopital's rule, we find another set of functions that gives us the indeterminate infinity divided by infinity, which really doesn't help us much. So what do we do here? Do we stop and give up? Well, no. What if these were the original functions given to us to evaluate? Would we have given up at step 1, or would we have applied L'Hopital's rule to this one? Let's try L'Hopital's rule again and see what we find. Oh, look at that, the limit is negative 2 divided by 3. And since the limit of this third step is negative 2 on 3, then the limit of step 2 must also be negative 2 on 3, and by extension of that, the limit of step 1 must also be negative 2 on 3. There is no limit to how many times we may apply L'Hopital's rule. Here we have differentiated twice, but we may differentiate again and again as many times as we like if necessary, although there does come a time in every young man's life where he must say to himself, L'Hopital's rule has been great, but now I must move on to more efficient means of evaluating limits. There are also times where L'Hopital's rule is inappropriate, such as this case right here. We could try to apply L'Hopital's rule, and by doing so we would find a new set of functions that are still indeterminate. After applying L'Hopital's rule again, we find ourselves right back to exactly where we started, and we can go on and on in this infinite loop forever and ever if we tried to force L'Hopital's rule to work. We would be much better off using basic algebra to factorize this function first and then finding the limit. L'Hopital's rule is an amazing tool in our arsenal. However, it is not bulletproof and it is not a one-size-fits-all rule. It must be used appropriately.